So now what I want to do today is talk a little bit about the relationship of velocity and acceleration. In terms of when an object is speeding up or slowing down. Okay, it's just another way of seeing what we should already know about velocity. When something's speeding up, the velocity is increasing, as we can see here. Velocity is getting larger and larger and larger. It's got one common rate, aka one common slope, which is one common acceleration, the constant acceleration that we have just calculated. In this case, it's 2 meters per second squared every second. Constant, constant, constant to infinity. So I want to go back here, and we're on the horizontal axis, and we know that in the horizontal axis, this is the east direction. These are all positive numbers. When we go below the zero, it's negative. That's west. We also have the acceleration here in the east. It's all positive, 2 meters per second, 2, 2, 2, 2. And what we notice is, something else I was going to say, but what can you say about, anybody want to take a guess at this? As this object is speeding up, what do you notice about the directions of velocity and acceleration on these graphs?
Well, as it's speeding up, it's not changing direction. Is that what you're looking for, maybe? I don't know.
Okay, is the direction being east or west? Okay, is the velocity and the acceleration in the same direction?
They're both pointing east.
Yes, they're both pointing east. They are both in the same direction. They're both in the same positive quadrant. So one thing we can say about when an object is speeding up, I'm just going to do a little side note here. Maybe I can just do this. Okay, for objects that are speeding up, accelerating, the velocity and acceleration vectors are pointing in the same direction. They're either going to be both east, both west, both north, or both south. We're in the y-axis. So a way to depict that via a motion map is, let's say do red for my velocity. So my velocity is getting larger and larger, larger, larger. Okay. I can make that a little bit better there. My eraser wants to work. Finally. Okay, so we have velocity getting just a little bit larger, and then, yeah. So that's my velocity. And then let's say my acceleration will be constant. We already see that the acceleration is constant by the graph that we saw before. The acceleration doesn't change, and they're pointing in the same direction. That's what we get from the graph. We make this conclusion based on other evidence. So one thing we can say about when an object is speeding up, oh, okay, the velocity and acceleration are in the same direction. In this case, they're both pointing east. They could both be pointing west. They could go north-south. So that's one thing that you'll see in your text there. I just wanted to talk about it a little bit. In this case, both the velocity and acceleration vectors are towards the east, or they're both positive. Now, of course, they could be both negative. I'll just do going to the west here as we depict west. Oops. A little bit more dramatic there. So I'm going to the negative x-axis in my configuration here. And so my acceleration, same direction as well. Object speeding up, but it's just to the west. Don't let the negative sign fool you. By the way, these are quote official notes. All right. Questions there. And meaning that if we took that graph in position time and we place it in the west, then we're going to have all of this data translate the same, but in the westerly direction. So as long as they're pointing in the same direction, the object will be speeding up. So that's the stipulation with a motion map to depict acceleration. Now, what we're about to see today is a slowing down case, because I want to start talking about a deceleration curve. And oh boy, laggy. So when an object is slowing down, the velocity and acceleration vectors are pointing in the opposite direction. You could probably infer that. Well, okay, speeding up is the same, slowing down, opposite. We're going to see that that is true. We're actually writing down our reasoning from a priori evidence, and then we're going to prove it ourselves. Let's see. So that looks like this. So another thing I want to say about the speeding up case, you know, realistically, you're putting your foot on the gas, you're peeling out, donuts, whatever. You know, you're speeding up, you're putting your foot on the gas to do that, right? Whatever you guys do to do your donuts. Your foot is on the gas, speeding up. And then here, you're on the brakes. The acceleration goes one way, and you go the other. Or velocity goes the other. So in that case, we see this picture here. Slowing down, we have, let's say, large velocity, and then steadily slowing down, right? Let's say that this is, well, this is going to the east. And then our acceleration will be going to the west at a constant rate. This is what happens when you put your foot on the gas. You are decelerating. You are braking. So one's going east, the other goes west. And we're about to prove that today. And the other case here, let's see, we have See if it's going this way, and slowly but surely. Okay, there's a negative velocity. Acceleration goes the opposite direction at a constant rate. So in terms of motion map, that's what we have. So make sure you have this guy down. Speeding up, slowing down. Okay, so I'm going to go back to, let's see, if I can share this extra screen. Okay. All right. All right. So what we're going to, you can pull this up, or you don't have to, but we're going to look back at this motion in a straight line, and we're going to generate this curve today, a deceleration curve. We know from prior lectures, or we're going to familiarize ourselves with this curve today, and we can see that the slopes, they're going to be different slopes because it's a curve, and those slopes are going to go from large positive to zero, large positive to zero, where this is going from zero to large positive. And so we're going to use a math equation to generate our values in velocity, and then from here we know it's going to be one slope, but the slope this time is going to be negative, and so that's why we're going to get this acceleration in the negative axis. And you can see just by the graphs that since this object is slowing down, the velocity and the acceleration are in different directions. This guy's in the east, even though he's getting smaller, he's still in the east domain, and this guy here is in the west domain. So graphically, we see what our conclusion states. You know, what we stated already, that when an object is slowing down, the velocity and accelerations are in opposite directions. And again, brake slowing down, and so forth. Okay, so back to, you guys good out there? Questions? You just chilling?
One thing, Mr. Kelly, I got the part for slowing down. Would you mind scrolling up? I didn't get to write down what you wrote underneath of speeding up.
Yeah. And tell me where.
That's good. Thank you.
Yeah. Okay. So make sure you guys have this, all of you. Let me know if I'm going too fast, too slow, whatever. Do not be shy. Okay. Let's now move on to generating our deceleration case from data table and position time to velocity time to acceleration time to graphing the data, taking slopes. I think what I'll do is I'll do the, I'll let you go to breakout because I think this will be fun for you. You stretch your minds a little bit. I'm going to generate the position time data, and I want you to go to your breakouts, and I want you to get your velocity time and acceleration time data using the patterns from before, using the same logic, because that's what you're going to do I'm going to go big time on your projects. I'm going to give everybody in your groups 3 sets of times. It's going to be 33 sets of times, such that everybody in your group is going to be generating a graph on their own, and that you guys can compare and contrast. Because I don't want this whole, one person in a group taking the weight. It's got to be distributed. And so paying attention now is going to make that life easier. Okay. All right. So we have our velocity and our acceleration and deceleration curves here. No problems from last time. Okay, now this is the object slowing down. We've seen the object speeding up. Speeding up. We have the curve going up. Now we have the curve going the opposite way. Not really a reflection. Well, it's not a reflection. Okay, so deceleration time. With a little bit of calculus, I generated this expression that we're going to be using to get all of our positions. And then from there, we're going to get our velocities. And then from there, we're going to get our accelerations. So we start off with this position as a function of time function. X of t, which is position as a function of time. You've seen this in math, y as a function of x. Same logic. Now we're doing real physical variables. And we're going to use this expression, negative t squared over 2 plus 15t. I get this from looking at that motion in straight line curve, taking the integral of that, and get this function. But don't worry about all that. Hey, we got a nice function and we're going to get some data. Hey, life easy. All right, so for t goes from 0 to 5 seconds. When we put t equals 0 in the equation, we're going to get, well, obviously 0. 0 squared over 2 plus 15 times 0. That's 0. So at t equals 0, x equals 0. So we're starting from 0, from ground, our conventional ground state. Now, so I should have done this like this. X of 0 equals this stuff here. So x, when t is equal to 1, what is my position going to be? Well, it's going to be negative 1 squared over 2 plus 15 times 1, or 15. You do that little math there, you're going to get 14.5. Let's call it 14.5 meters, because our conventional unit of position and distance or displacement is the meter. And then we can get all different forms of meters, decimeters, and all that stuff if we want to, whenever. So the position is 14.5. Now, x, when t is equal to 2, is going to be negative 2 squared over 2 plus 15 times 2, which is 30. And that's going to give me 28. You can verify that for yourself. Go ahead, make sure. And position when t is equal to 3, negative 3 squared over 2 plus 15 times 3. That will give me 40.5. You can probably start seeing the gaps looking like something, kind of a little pattern going on there. And then x is a function of 4, or when t is equal to 4, plus 60. Why is that? Okay, let me just make sure. Where does 60 come from? 15 times 4. If there's anybody asking that. That will give 52. And then when t is equal to 5, That's going to be -5 squared of 25 over 2 plus 15 times 5 equals 62.5. So this is important in generating data for your projects going forward or for anything, period. You start off with a general function. In our case, we have to start off with a general function because we're not able to go to the lab to actually generate actual positions for every time and then generate a function from that. That's the conventional way of getting that function, because once we grab all of our data and put it together in a data table and then graph it, then we can use our skills in trigonometry to get an equation of this curve. If you guys recall how to do that, I wouldn't have you do that, but you could use that skill here. But since we don't have the lab apparatus, that's why, okay, give you the function first. We're going to generate some arbitrary, well, data that's going to work. Theoretical, like as if we're doing an experiment theoretically, it's going to be a theoretical experiment. And then we're going to put this data into a position timetable. Then from there, we're going to take the slopes, and then those slopes will be velocities. And then we're going to take the slopes of the velocity timetable, and those slopes will be accelerations. So let me just get you started here. So for every second, 0, 1, 2, 3, 4, 5, we have generated data. This is our mock experiment. We've done the experiment mathematically, you know, so to speak. So the physical experiment, well, we'd have to be in the class, and that would be our real experiment. Okay, so position time data table looks like this. Again, we've seen this over and over. So when t equals 0, position is 0. We saw that on the deceleration curve. It starts right at the 0. Our first data point, well, when time is equal to 1, we get 14.5. And then 2, we get 28. 3, 40.5. 4, 52. 5, 62.5. That's how we populate our data table through the math. Else in the lab, we generate it by, you know, you guys put the popsicle sticks down for every second, like we saw in that one video, and then you generate your data table. But this is also pretty cool. I hope you will find. Now, again, definition-wise, the slope of this position time table gives me what quantity? Anybody? When I take the slopes, what am I generating physically?
The velocity.
The velocity.
Yeah, right. Excellent, Sophia and Lala. Yes, I'm generating velocities. Do you think I'm going to have one velocity or many velocities?
Many.
Many.
Yes. Why many? Yes.
It's not constant.
Right. The gaps are unequal. So we're going to get different velocities for every point. So that's what we're going to do now. I want you to go to your breakouts. Breakout. Okay, and what I want you to do is I want you to generate your VT and AT data tables. Okay, you could then, you know, and so let's see, so I can verify that. I want you to do that, and this will be subject to, you know, being turned in.
Would you go up a little bit? I didn't see that.
You tell me where.
Under the graph, under the thing. No, not the graph, the chart. Sorry.
Right here.
Yeah, thank you.
Okay. Yeah. Yeah. Where I was. All right. So you want to generate VT and AT data tables. What I want you to do is, from getting the VT, that's going to be the slope of your XT. So you can say S1, this is what I would like you to do. I want you to calculate the slopes, the actual slopes between two data points. And then I also want you to, those slopes are going to actually be the velocities. So let's say this is a sample slope. Again, this is not for your data. Let's say 5 minus 0 over 1 minus 0. That slope is just 5. But in velocity terms, that's going to be, something like that, because it's positive. So this first slope corresponds to a first velocity at 0. Okay. So just to be another reminder. So when you take this first slope, 14.5 minus 0 over 1 minus 0, that'll be 14.5 at 0 seconds in the velocity time graph. Okay. And then you're going to populate all of the other velocities at the different times, 1, 2, 3, 4, 5. All right, so I want you, that's what I want you to do for both getting your velocities and also your accelerations. Let's say your first slope in acceleration would be something like, I don't know. Again, this is example, pure example, not relative to data. That'd be 7. And then that corresponds to your first acceleration being positive 7 meters per second squared, because the slopes of VT gives me my acceleration. So I'm going to be even more specific with that. And so the slope of, my XT, my first XT data points gives me my velocity, my first velocity. And then you don't have to write this, but this is just another way of just grouping and ordering the information so you know exactly what you're looking at. So this, the first slope of your VT data gives me my first acceleration, stuff like that. That's an option, but I do want it in this form. I want you to calculate the slopes of each data points and translate them to a velocity or acceleration. Questions before we break out?
I just have one question, Mr. Kelly. So you said, so like for the first case, for example, it would be 14.5 minus 0 over 1 minus 0.
Mhm.
Then would that be the velocity at 0 seconds or
At
1
zero.
second?
At 0.
0 seconds. Okay.
Mm-hmm. Yeah, because that's, yes.
All right. Thank you.
Mm-hmm. All right, so let's get going. Different format here. Let's put you. Let's do. I have 3 to 4 people, and hopefully lets me. Okay, good. Options. So since there's a lot of data to generate, let me give you about 25. I'll give you about 20 minutes. Okay, see you in about 20. Thanks. All right, Anthony, Miriam, let's go. Cameron, let's go. Any ideas? When is the acceleration positive? Phone a friend. Let's see. Anybody want to step up, volunteer? Who hasn't spoken? Who wants to tell us when is the acceleration positive?
The acceleration.
Me?
Oh,
Hey,
you go.
Yeah, not Miles or Lala. Someone else.
Me?
Romero, yes.
Uh,
What?
It's B, right? Or okay, so like
Yeah,
acceleration is most positive in the first 5 seconds. So like 0 to 5 seconds.
perfect. All right, because the slope of velocity time is the acceleration. So therefore, the acceleration is positive from 0 to 5 because the slope is positive from 0 to 5. In velocity time, when is the train's acceleration most negative? Sophia Lorenzo, what you got for us? When is it most negative? Or you can tell me any time interval when the acceleration is negative, period. If you can. Rita, what you got? Oh, okay, see, she answered finally. Or some. I didn't call on you. But you know, if you're gonna speak up, okay, Alex K, yeah, you're correct. Alex says 15 to 20. Is he right? Anyone? Acceleration
right.
negative? That is correct.
Yes.
Yes. All right, so that's credit. And what we got? Yeah, you're Alex K. Yes, he's right. Okay, let me mark this down so you don't. Trying to. Okay, so Alex. Okay, now let's see if something real quick. 42 minutes. Okay, and now it's gonna be a challenge. You gotta give me a challenge sometimes. Okay, let's go here. Example problem. So we have this ball's motion going up slant driveway, da 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 da. What I want to ask anybody here is, which of these arrows shows the object slowing down and why? Let's go with Rita.
I think the first red one, because the gaps are becoming smaller. The arrows are smaller, becoming smaller. So the velocity is like decreasing too. So it's slowing down.
Yeah, exactly. So the velocities are getting smaller. The arrows are getting smaller. You can see the gaps. You know, the arrows representing the gaps are getting smaller, and also too, there's another reason too. So let's go with. But that's perfect. Mark, Is there another reason why you can tell the red arrows are slowing down relative to acceleration? Okay, we got a private chat. Pointing left. What is pointing left? The acceleration, right? So they're going in opposite directions. So as we just defined, that an object is slowing down when velocity and acceleration arrows are opposite directions. And so therefore, this has got to be speeding up. So he's going to, when he goes up here, he's getting slowing down, and he changes direction, comes back down, he's going to be speeding up. Okay, example, 5 to 10. Yeah, I think I just had you guys stop at 10, right? 1 through 10.
Yeah.
Okay. Yeah. So that will be that. Let's take a, while we yet have time, I want to see if we can peer onto the free fall stuff, because I'd like to try and wrap motion and constant acceleration. So yeah, I'll be giving you guys some of this next. So you're returning that 1 through 10 today. And then for Friday, I want to try and wrap up things before Thanksgiving here. So on Friday, what we will do is we can go over some of these problems in class, like breakout / in class. So let's do a bunch of these, and not just on this section 2, but also section 3. I think I double clicked this thing. Okay. All right, going back. So I want to do some free fall. So Friday I want to do section 2 and 3. Get to some free fall. So free fall is just taking those equations. You if you recall those equations that we grouped the 8 equations together, and the equations on the right, the equations in the y direction are the equations for the y-axis, or free fall. Free fall, which is due to acceleration of gravity. So let's see if there's any problems here. Yeah, there's a few. We'll work on those as well. So we're just going to be doing problem solving, wrap things up, talk about variations in free fall, and that'll be basically it for acceleration. After Thanksgiving, we'll start forces, which is module 3. So let's take a look at that. Standard work, and, roller coasters, wrap up. And module 4, module 3, that module 4, forces. Okay, we'll be doing balanced and unbalanced forces. Force and motion. What is a force? We'll develop our understanding of that. Come into the book here and take a look at things. As you can see here, what's happening to the object here? Speeding up or slowing down?
It would be speeding up.
Yes. Why? Not the gaps. Give me the reason we were talking about today. The gaps as well too, but in terms of what we talked about today, why is it speeding up?
Velocity and acceleration are in the same direction.
Yes, perfect. Thank you, Rita. Yeah. So yeah, the velocity acceleration in the same direction. When their opposite direction is slowing down. And in this case, with forces, what we're going to be doing is we're going to be analyzing the cause of motion, which are forces. So before we were looking at just motion, period, motion equations, motion kinematics equations. And now we're going to start taking a look at what actually causes things to move, what actually causes things to accelerate, or even move at a constant speed. It's all about the forces. And then from there, we're going to go to energy. From there, we go to momentum, and so on. Because now the physical universe starts building up, starts expanding, if you will, conceptually. Okay, so that is that. Any questions on the homework that's due today? Like any, we don't have time to, or a problem, but You know it's due today.
So we're turning in the work we did today, classwork with the homework?
The work we'll do today is going to be notes for 11/17, and then the homework will be turned in later on today.
Okay.
Mhm. Okay. So, yeah, so there. All right, so let me get to a question here. The homework due time is on the stream page. Hey.